Now previously, we explained for the case of Riemann surface of genus 1, i.e. elliptic curves, why the periods uniquely determine its isomorphism class. That is because of this period mapping, which is defined as follows. We pick a basis, omega, of this space of holomorphic one form on E. Then we fix the point P0. The period mapping sends every point P to the integral from P0 to P of omega. This is not well defined because there are many paths from P0 to P. It's only defined up to integral over a loop. So its value should lie in this torus. This is the quotient of C by the integral of omega over loops. These turns out to form a lattice called a period lattice because the homology class, first homology class of E, is generated by two elements. So we can write every homology class as a linear combination, integral linear combinations of these two basic loops. So the period lattice is the lattice generated by these two integral. From now on, we will write it like this for simplicity. This is implicitly understood to be generated as a Z module. Okay, and this map turns out to be an isomorphism. So that means these periods uniquely determine the isomorphism class of the elliptic curve. Now let's generalize this map to the case of a bigger genus. So now the space of holomorphic one form will have bigger dimension. If the genus is G, then the dimension of this space is also G. So a basis should consist of G one form. So let's take omega 1 omega G. And our map then will send every point P to this tuple. Again, these are not well-defined complex numbers. So we have to quotient out the value of these integral over loops. Now, when this surface is of genus G, i.e. it's a G-hole torus, then the rank of this homology group is going to be 2G. It's going to be generated by some gamma 1, gamma 2G. Let's choose that as a base. Then this integral is a well-defined point in this quotient. By this, we are denoting the Z module generated by this integral over this basis. So, is this map an isomorphism, like in the case of genus 1? If we look at it carefully, we will anticipate that that couldn't be, because this has a natural structure of an abelian variety, but in general, for a general Riemann surface of genus G, there's no natural group structure. That's why elliptic curves are so nice, because they have a natural group structures. You don't see that every day. You don't see that with just any Riemann surface. This is actually in a sense, the best fit abelian variety associated to X. So of course it has a name. It's called the Albanese variety of X, and it has a coordinate-free description. We can view it as a dual space of the space of holomorphic one form, mod out by the periods. Right, so how are these the same thing? And how do we define this map in terms of this? Well, in terms of this coordinate-free description, this map is going to be given by P mapping to this linear functional. As you see, this linear functional is uniquely determined by its value on a basis of omega 1. So giving this piece of information, these G numbers, is equivalent to giving this linear functional. Also, even though we don't have an isomorphism here, we do have an isomorphism if we change this map a bit. We can extend this map to divisors on X by linearity, and actually we'll restrict that to the case of divisors of degree 0. Then it turns out that the kernel of this consists of all the principal divisors. This map actually turns out to be an isomorphism, and this group has a special name. It's the Picard variety of X. So even though we don't have an isomorphism between X and its Albanese variety, we do have an isomorphism between its Picard variety and its Albanese variety. Note that this will only work in dimension 1. In higher dimensions, these two varieties are dual, but not necessarily isomorphic. Okay, so that's all good, but you're probably frustrated now because we said that we're going to talk about how the periods determine the Riemann surface, and here it seems that the periods here determine the Picard variety of the Riemann surface. We haven't talked about the relationship between the periods and the isomorphism class of the Riemann surface. So let's do that. This claim is gonna be implied by Torelli's theorem. To each Riemann surface of genus G, we can associate a matrix called a period matrix. So what are its entries? Now its entries are just going to be these basic period. We take a basis for the one homology group, and then we take a basis for the holomorphic one forms. And each of this entry is going to be the integral of one of this form with the homology class. So what we get is called a period matrix of X. Now Toreri's theorem basically says that if the period matrix of X and the period matrix of X prime are the same, then X and X prime must be isomorphic. But not really. You're probably a bit confused about this statement, and that's very understandable, because this is not really well defined, because the period matrix is not canonical. It depends on a choice of basis here. So when we say they are equal, we have to say with respect to which basis. So we have to add the condition that we want to choose a basis of one homology classes here and here in X prime in such a way that the intersection number agree. This is the intersection form over X, and this is over X prime. Once we have chosen such a basis and formed period matrices, then if the period matrix of X is equal to the period matrix of X prime, X must be isomorphic to X prime. And that is how periods determine the isomorphism class of a Riemann surface. So that's for projective variety, non-singular projective variety of dimension 1. We will look at the case of non-singular projective variety of higher dimension in the next video.